Hey guys, welcome to another video. Today's learning objective is to calculate or estimate gradients of graphs and errors under graphs, including quadratic and other non-linear graphs, and interpret results in cases such as distance time graphs, velocity time graphs, and graphs in financial context. Before we get started, as usual, feel free to skip to any part of the video. Timestamps are here, thanks to the magic of editing. The stuff that we do need to know, prerequisite knowledge in this kind of stuff, is really important to have seen the last videos where I talked a bit about using gradients and using graphs in real world context in a bit of a user situation. This is a kind of a higher only video, that's what's in purple. But yeah, let's get into it. Quick thing here is the word velocity. If you haven't seen it before, it's kind of another physics way of saying speed in a brief way, a generalized, not generalized, but kind of as a more simplistic way. You can just think of it as the same thing as speed. There's a few other differences, which I'll kind of talk a bit more about at the end as kind of a bonus. I don't think you really need to know that in that much detail, but it might be helpful if you know the difference. But basically, you can think of velocity as just a speed. Let's think about something like this distance time graph. And we can see here if we look at the gradient, which if we remember from the last video is the speed, we can see how the speed of the speed and the gradient, which are the same thing, is increasing in this case. So you can see the gradient is pretty shallow here, but pretty steep up here, right? And that tells us that the gradient is increasing. And perhaps what this might be like is say a sprinter. So say Usain Bolt, for example. And funny enough, we've got a video of Usain Bolt right here. So I think it's in German. Yeah. And you can see how Usain Bolt is actually speeding up so when he starts off back here, he's kind of stood still, right? So his speed right now is 0, but when he's got his goal, beating the world record, he's going really quite quickly, right? So that's an example of how he starts up at the quite slowly, and then just starts speeding up. And what we might think about what's Usain Bolt's speed, right? Well, we know that he covers 100 meters. This is a 100-meter race in 9.58 seconds. That's that world record. So his speed, Usain. So I'll just write speed. And we know speed is distance over time, right? So he covers 100 meters in 9.58 seconds. So you can say his speed is this, right? And that's his speed over the whole thing. But we've already established that his speed is actually increasing throughout the whole thing. So we'll actually call this the average speed. Because over the whole thing, over the whole 100 meters, he took 9.58 seconds. But for the first, say, 10 meters, he's a lot slower than the last 10 meters, remember? Because he's speeding up. So we think of this in and if we make that distance, say, instead of 10 meters, we may say 1 meter, or not even 1 meter, we think maybe half a meter, or maybe a centimeter. And we get to this idea of instantaneous speed. So your speed at a certain instant. So, for example, we know that we know that Usain Bolt's speed when he crosses the finish line is 37.6 kilometers per hour. So that's saying his speed right at the end, for example. And his speed right at the beginning, just when he's starting, might be 0, and then it increases. So at that very second that he crosses the finish line, his speed is 37.6 kilometers per hour. So that's what the idea of instantaneous speed is. So instead of thinking of a huge amount of distance, say 100 meters, we start thinking of smaller and smaller and smaller and smaller distances till we get that exact spot, basically. It's a bit of a harder concept to get your head around, but just know instantaneous, you can find, instead of thinking of the gradient over a larger period, you can think of the gradient at a point. So if you think of the gradient at a point right here, that's the speed at the instantaneous speed at exactly this time, whatever that time is. If you think of the gradient at that point, so I'll just write gradient at that point, at point X, for example. So now that we've got this idea of instantaneous speed, or the gradient at a point rather than the gradient over a range. So instead of thinking of the gradient as from in a straight line, for example, we have a gradient over from here to here, right? for example. But in this kind of a curved line, we start to think of gradient at a certain point. And the way we calculate that is kind of by drawing something, by drawing a tangent. It's this, look. This is kind of the gradient at a point. If I zoom in, you can see at this certain point, you know, that's what the kind of the gradient, if it was the gradient of this line was to continue at this point, kind of forever, that's what the line would look like. So what you do is you bring your ruler up, you look at this point, and you say kind of it just touches the line, and you draw this, you know, extended line out, and then you just calculate the gradient of this line, which is called the tangent. So for example, this is a question of being asked to calculate the gradient of y equals x squared, which is what we know is quadratic, at the point x equals 3. So what they've done is kind of they've taken the ruler out, they've kind of brought it up so that the line just touches x equals 3, and kind of, if you zoom in, it's at the same kind of angle or the same gradient as, you know, around what x equals 3 is. Kind of, it's supposed to be at that point exactly, but you can't kind of look exactly at that point. You can't zoom in so far that it's going to be exactly at that point. So you just say kind of at around that point, so around like in this vicinity, basically, that the line is going to be touching and kind of the same gradient. And then you just extend it out like this with a ruler, and then say kind of, you know, pick your points and do kind of change in y and change in x. Which is kind of, you know, what a regular thing is. Really important again, have like a sharp pencil to make sure kind of you have a thin line, or else like sometimes it's a bit harder to read the values of. And then kind of with these, you know, I struggled a lot with finding the gradient because, you know, whenever I do, I'd get the tangent a bit off, and kind of, you know, maybe it would be touching the line too much or not enough or something like that. So again, really important you practice loads of these and just get better at finding these tangents. It's a bit of a skill rather than, you know, a mathematical thing. It's kind of just something you have to do so many times that you finally get good at drawing a nice line. That's basically all there is to it. Again, really important you do practice this. So let's do kind of this question here, right? I'm actually just gonna, ooh, okay. Sorry, I had the wrong question with the wrong graph. So this question is, you know, I'm just going to do the final part of the question of, so the graph above represents the velocity of the car for 30 seconds. And, you know, what does the gradient represent? Well, remember the gradient of the velocity time graph is acceleration. We've, you know, just remember that. And then the question is, say, for example, if you're asked to find the gradient at a certain point, so say, like here, estimate the gradient at 16 seconds, correct to one decimal place. So again, what we do is we go up to 16 seconds, you can, for example, mark it, and you get your ruler out. I'll do the best I can with this. And they say, look, you know, you have to pass through that point and be roughly at that gradient, right? You can see how that there's a gradient there, right? And you can say, oh, yeah, I don't think this is going to look too, so yeah, this might not look too great, but I'll try my best. Okay, I don't know why it's doing that, but okay, there's a, you know, this is drawn out for me, thankfully, to save me the pain of doing that, on this kind of machine, this laptop. So kind of, yeah, this is done so that you draw a tangent like this, and you pick, say, the values you want, so say 25 here, and then this, what is that, 8, and then, so the values are 8, 0, and 25, we go along, 15. So the gradient at that point, for this question, estimate the gradient is change in y, which is 15 minus 0 over 25 minus 8, which is 15 over, what is that, 17? Which comes out to, which I'll just use my calculator for this. 0.88235 to 1 dp, which is all we need, so that's 0.8823 If you round to 1 dp, that just comes 0.91 dp, and we need units, right? And for acceleration, the units is meters per second squared. So again, what is the the tangent at 16 represent? Well, that's the gradient exactly at when time equals 16, and the gradient here is the acceleration, right? So that means that's the instantaneous acceleration at t equals 16. So that's what you say. You say, you know, compare. So what does the gradient represent? We know it's acceleration, and at t equals 16, that's the acceleration at time equals 16. And then if you compare it with the average gradient, which is again drawn out for you, you can say that the average gradient is actually a bit steeper than the sorry. You can see that the average gradient is a bit steeper than the tangent gradient. So that means that the acceleration at t equals 16 is less than the acceleration like over the larger period of time, over the average acceleration, because the average gradient, that's the average acceleration, but this is less steep, so therefore acceleration at t equals 16 is less than average. And what is happening over time? Well, you can see how the gradient is increasing, right? And remember, the gradient is the acceleration, so you can say the car is accelerating. So yeah, that's kind of how you calculate the gradient of kind of a certain point, and that kind of the gradient at that certain point is basically saying kind of the instantaneous velocity, the instantaneous speed or acceleration in this case, of kind of the thing kind of at that exact point. So remember, we can think of kind of a big, acceleration speed over a kind of a big amount of time. So say with Usain Bolt over his whole 9.58 seconds, the speed changes. So we can think of his average speed over that whole time, or we can think of his speed at a certain point, like when he's crossing the finish line, for example. So that's how, and this is how you do it. So just in general as well, right? Kind of, you can think of the value of the gradient is the same thing, right? As if it was a straight line. If it was a velocity time graph with the same line, a straight line, it'd be an acceleration, right? The gradient, and again, the same thing holds even if it's curved. But just remember, since the gradient is changing, you have kind of instantaneous acceleration in this case. Okay, we've got another question. So the graph shows the velocity of the car over 8 seconds. This actually isn't here, this question here, but so what would the gradient here represent? Well, if it's velocity time, as again, that's acceleration again, and then say if it was the gradient at say time equals 4, that'd be the instantaneous acceleration at time equals 4. Now it's asked us to estimate the area of the curve underneath between 2 and 6 seconds using 4 strips. So you go, if there's 2 and 6 and you need to use 4 strips, right? What you do is kind of you divide 2 and 6 into 4 like equal parts. So this is 1 part, this is 2 parts, 3 parts, 4 parts. So you can kind of tell it's going to be like that. So you kind of, what you then do is you kind of pull a line up, I guess. And the thing you tend to do is you draw a straight line between these 2 points, like that, and you get a trapezium. And you do the same thing here. Again, between these 2 lines, that will be a trapezium like that. And again, same thing here. So obviously with a straight line, again in this case it's a bit harder. And then you calculate the area of each trapezium. So you calculate the area of this trapezium, plus this, and plus that, to get your full kind of the area under the curve. So the way you do it, so they'll tell you how many strips to use, and if they don't, I guess it's a fair assumption to say kind of between kind of these thick lines. I guess that's a fair assumption to use if they don't kind of give you one, but they do. They will usually tell you how many strips. And when you do that, you have these 1, 2, 3, 4, 5, 4 strips, and then you kind of draw a line up to here, and then connect the two, kind of this point with this point, using a straight line to form a trapezium. And then you just use our usual kind of area of a trapezium to to find the area of this plus the area of this plus the area of this plus the area of this. So in this case, the area of a trapezium is a half a plus b times by height. So if the trapezium is something like this, and this is a, this is b, and this is height. So the height in this case is 3 minus 2, which is 1. A is, if we zoom in a bit, when it's 2, so what is that? 13. B is 15, 16, 17, 18, 19. So 13, 19. So the area of this first trapezium is a half a plus b, so 19 plus 13, times by height, which is 1, which is 19 plus 13 divided by 2, which is 16. And then you do the same thing for this one, for this one, for this one, and you just add them all up to get an answer. And then if you kind of, there's actually a bit of a shortcut. Instead of doing each of these separately, what you do is that you use this formula here. The area is kind of h, if you look at it here, it's notated, h over 2, y naught plus 2, all of that. And you don't necessarily need to know this formula. You can do it the way I've said it. This is just a bit quicker. And if you think about the logic behind this, right, why it's this. Well, the area of this first trapezium is a is equal to a half y naught plus y1 times by h. And then the area of the second trapezium is, so I'll say a1, a2 is equal to a half y1 plus y2 times by h. And if you and you repeat that, but if you add, let's say, a1 plus a2 up, is equal to, so you got half y0 plus y1 times by h plus a half y1 plus y2 times by h. Let's factorize out the half times h, so which equals a half h into y0 plus y1 plus y1 plus y2, which comes out to half h y0 plus 2 y1 plus y0. And you can see if we kind of repeat this, right, if we have over 4, for example, these middle ones are used twice in the calculation. You use it, say, to find the area of this left-hand trapezium, and then again on this right-hand trapezium. And if you if you were to do this whole thing, you'd again use this y2 to calculate the area of this one, and you use different colors to. So y1 you'd use for here and here. y2, for example, you'd use for this left hand and this right hand, and then the same thing with y3, left hand and right hand. Same thing with y4. But if you see with y5, for example, it's only used for this left hand, so it's only used once. And same thing with y0, it's only used once here. So that's why it's kind of y0 here and yn, as in the last one here, because they're only used once and they're not multiplied by 2 like the rest of these. So this is just a formula you might want to learn if you you might find this a bit helpful to learn this and memorize this. Instead of kind of calculating the areas, by finding the area of a trapezium in division and adding them up. And then what does the area under the curve represent? Answer to 1. Well, it's a velocity time graph. Remember that just represents distance. Let me choose black by pen. And now the question is this an overestimate or an underestimate? Justify your answer. Okay, so this would be a bit helpful if I had drawn this a bit better, so I actually will. Okay. When we let's zoom in a bit more. When we connect this line to this line, you can kind of see how the trapezium is actually above the line, and you can see this with here as well, right? You can see it's a bit thick of a pen, so you can't really see, but you can see how there's this bit left open, right? And there's that bit, so you can see how it's above how our trapezium is kind of always above the line. Okay, that's very badly drawn, but So yeah, I'm not going to bother drawing that. It's not going to look very good. But you can see how it repeated. It would always be above the line. So that means the area we estimate with trapeziums is greater than the area underneath the curve. And that the area so the area underneath the curve, this is actually the true value, and we're approximating it by kind of using these trapeziums, right? And since our trapezium stuff is more than the true answer, so it's an overestimate then. So our answer is overestimate. And justify your answer, you justify it like this, being like the trapeziums are always above the line, so it's an overestimate. And that's kind of all there is to it. So yeah, hopefully that kind of all made sense. It was kind of this topic is just kind of very much kind of using your pencil and kind of drawing stuff, and in that sense, there's a lot of silly mistakes to be made. There's not too much kind of theory behind it. Just make sure you kind of remember how to draw this stuff out, and it's really helpful to practice this. Print off a few questions like this and try it out, kind of draw a line, see what happens, and kind of calculate the area. And hopefully, yeah, that all made sense. And I'll see you guys in the next video.